Hello, friend. I'm glad you found a quiet shore of the night. Let the day set behind you like a fading tide, and sink into the pillow as your breath finds an easy rhythm. This is a small, lamplit room for curious minds and tired hearts, where science speaks in a whisper, and nothing demands to be solved before sleep. Tonight we'll wander gently into a candlelit corner of physics, where the ordinary rules soften and a deeper, quieter script appears. It's the quantum place so delicate and surprising that even seasoned scientists grow hushed. Particles blur into waves, causes and effects seem slightly out of step, and reality feels less like a brick wall and more like a curtain stirred by the lightest breeze. We won't rush. We'll hold the mystery lightly, the way you cradle a fragile ornament, turning it just enough to catch a glimmer. If these calm night journeys help you drift, a soft tap on like and subscribe is a small kindness that helps other sleepy travelers find this room without breaking the hush. Now, let your eyes grow heavy. I'll keep the pace unhurried and the edges rounded as we step into the quantum dark, where worry loosens and wonder stays. Let's begin. Most days, the world behaves like an old, reliable clock. You press a switch and a lamp glows. Keys slip from your hand and meet the floor without drama. You close your eyes, open them again, and the room has remained itself, politely waiting. Causes line up with effects. Actions build their quiet reactions. One thing leads cleanly to the next. It's a kind of trust we learn early and rarely question. Then the tiny world speaks, and the tone changes. Stories arrive from laboratories about particles that seem to be here and also there, as if a coin could rest on two different tables at once. Measurements that look as though a choice made now leans back and brushes the past. Properties that loosen from their objects like dandelion seeds and drift apart. Two careful observers watch the same event and come away with truths that don't perfectly overlap. At first, it's tempting to blame the symbols on the page, to call it math's mischief, clever abstractions, floating far from anything with weight or warmth. Digging deeper doesn't return you to safety. It opens a door. The reports are not daydreams. They are experiments, done carefully, repeated patiently, refined by generations of steady hands. Different teams, different places, different years, and yet the same strange results. The measurements are not being careless. The instruments are not blinking. The weirdness keeps showing up not as a mistake but as a feature, like grain in wood. What you're seeing is the way nature carries itself when you look closely enough. This is where the word paradox enters in a new costume. Not a clever riddle with a wink and a hidden latch, but a road sign planted where our understanding thins. These are the creases in the map, the places where the lines we drew for comfort don't quite match the landscape. They aren't meant to frustrate, they're meant to point. They tell us that our picture good, useful, beloved may be missing a layer. In the world you can throw and catch, everything feels settled. A baseball leaves your hand and climbs, slows, and arcs back down. You may not know the exact landing spot without the numbers, wind, spin, the strength of the throw, but the ball is always somewhere definite on that path, moving with a speed that could, in principle, be written down. With enough information, the future of that ball follows from the present. That was the harmony Newton taught, a clockwork universe, cause by cause, gear by gear, where objects have properties whether or not anyone is watching. Einstein widened the room. He showed that space and time are woven, that gravity is not a pull but a bend, that clocks and rulers are loyal to motion and mass. It is a stranger universe than Newton pictured, but its strangeness still fits together. Given the state of things now, the later state follows, dilated here, curved there, but connected by a line that doesn't break. It is causal. It is real in the everyday sense. The moon is the moon whether or not you glance up. Then, the quantum story stood up and cleared its throat. At the scale of atoms and the particles inside them, nature behaves like a musician who can play two notes at once. A particle can occupy a blend of possibilities, as if it keeps more than one itinerary open. Looking at it gently, carefully, does not just reveal a pre-written answer. The look itself is part of the script. Two particles can separate by miles and still share a connection that doesn't ride any signal we know how to send. None of this is a confession of ignorance or a smudge in a notebook. It is the pattern that refused to go away no matter how crisp the experiment became. From that stubborn pattern, a theory was written. Quantum mechanics does not flatter our instinct for clocks and gears, but it tells the truth with astonishing accuracy. Its predictions arrive with absurd precision, digits upon digits that match what we measure. It underpins the behavior of atoms, the building of molecules, the quiet rules of chemistry itself. The glow of LEDs, the rhythm of lasers, the logic gates in the chip that brings this voice to you, each depends on quantum rules. The timing in GPS relies on quantum-tuned clocks. The images inside an MRI are painted with quantum spins. If you gathered the tools of today's world and shook them gently, quantum principles would ring like coins in a bowl. And yet the signposts remain. Some questions have been carried for decades like smooth stones in a pocket. What, precisely, is a measurement? Does the world carry definite properties all along? Or do properties crystallize when we look? How can distant partners keep step without exchanging messages? Why do probabilities numbers meant for uncertainty behave as if they are part of the fabric rather than a shadow of ignorance? Different camps offer different portraits. Some keep the world deterministic under the floorboards. Some let reality branch like a forest at night. Some add a soft randomness. Some hide variables in deeper folds. Each portrait saves certain intuitions and spins others. It can sound alarming to say that foundations have cracks, but the word is kinder than it seems. Cracks let in light. They show where to reinforce, where to rethink, where to be humble. In the realm of the ordinary, your trust is safe. Lamps switch on, keys fall, baseballs arc. In the small, quiet realm underneath, trust wears a subtler face. The rules are not broken, they are different, like currents under a calm surface, and learning their flow has given us the modern world. The plan is simple in spirit and slow in pace. Treat these paradoxes as invitations, not threats. Set them on the table like delicate instruments and listen for their shared notes. Let the math stay softly backstage while we bring forward only the shapes it suggests, the way possibilities spread and narrow, the way connection can be invisible yet firm, the way looking and being looked at become part of the same dance. No rush, no sharp edges, nothing that demands an answer before sleep. Just enough clarity to rest in, just enough wonder to keep the room gently lit. Keeping that cadence, the next note is easy to hear. Most of the strangeness comes from a simple mismatch. The equations steer like expert navigators, delivering us to the right harbor again and again, while our picture of the night sea keeps slipping through our fingers. Quantum theory tells us how to compute the odds, when the detector will click, how the statistics will stack up hour after hour. It sketches circuits for quantum chips, sets the tempo for lasers, whispers which designs will sing. What it doesn't hand over, at least not neatly, is a clear portrait of what's out there when no instrument is watching. Are particles tiny pebbles or waves of possibility, or something quieter with no perfect analogy? Do properties sit patiently on the shelf waiting to be measured, or do they crystallize only when the act of measuring becomes part of the story? Step from calculation to meaning, and the floor creaks. Questions that felt harmless start producing contradictions with sharp little edges. Ask whether a particle carries a definite path before anyone looks, and the answers begin to tug in opposite directions. Ask how two partners can remain correlated across a room, a city, a planet, with no whisper passing between them, and the usual picture of causes marching locally from place to place looks suddenly underdressed for the weather. The elders who built this house heard those floorboards too. Richard Feynman, so deft with diagrams and wit, admitted that no one truly understands quantum mechanics in the ordinary sense. The theory works, but it won't sit still for a tidy explanation. Niels Bohr, steady as a lighthouse, warned that if quantum theory doesn't shock you a little, you've missed the point. Roger Penrose, no stranger to hard geometry at the edge of black holes, has said bluntly that the theory, as commonly read, makes very little sense. Albert Einstein, who helped light the fuse with the photoelectric effect, kept insisting the story must be incomplete. That chance could not be the final author. Dice, he joked, were not the creator's style. Even Erwin Schrödinger, father of the famous wave equation, later confessed discomfort, as if the cat he imagined would not leave the room of his thoughts. These were not timid minds. They were the very people who invented the machinery, tested it until it rang true, and then found themselves lying awake with the implications. Decades have passed. The experiments got cleaner. The digits of precision stacked higher. Quantum technologies grew from sketches into factories, and still the core questions remain on the bedside table like a glass of water at midnight. What exactly is a measurement? What does the wave function describe? A book of probabilities, or a field as real as the air, or something we haven't named? Do unobserved systems carry the properties we later find, or do properties arise in the meeting between system and apparatus? How does the shimmering, many possible micro-world settle into the firm, one-outcome world where coffee is either spilled or not? These are not ornamental puzzles. They mark the boundaries of where explanation ends and mystery begins. Follow them, and you find your intuitions bending. Time may not feel as one way as a river. Observing may be less like watching a stage and more like joining the play. Reality may arrive as a pattern that depends on how it is asked to show itself. Particles may be less like dots and more like diffuse likelihoods that tighten under attention. In other corners, information behaves like a sacred quantity, refusing to vanish, even at the mouth of a black hole. Some thinkers, careful and sober, have wondered whether awareness, consciousness, belongs somewhere in this circle, not as magic, but as a participant whose role is still poorly drawn. It sounds mystical until you notice that these questions arise not from incense and metaphor, but from laboratory data and proofs written line by line on chalkboards. The power of these paradoxes is in how stubbornly ordinary tools bounce off them. Better detectors sharpen the picture. They do not dissolve the contradictions. More careful setups change the noise level. They do not unbraid the logical knots. The puzzles seem baked into the logical structure of the theory itself, as if the equations are hinting at a deeper layer that our current language can only gesture toward. When history rhymes, it often uses paradox as the rhyme scheme. Oddities in planetary motion opened the road to Newton. Inconsistencies in electromagnetism and the behavior of light led to relativity. spectral lines and thermal radiation cracked open the quantum era. Each time, the paradox was not a wall, but a doorway. Perhaps the present door leads to a framework that leaves quantum mechanics intact for all the things it already does brilliantly, while explaining why it wears the shapes it does: superposition, entanglement. The crisp click of outcomes produced from blurry possibilities. Perhaps the needed move is subtler, a shift in the way we talk about information, or causality, or what counts as real before a question is asked. Or perhaps the lesson is more radical, that nature is not obliged to soothe our classical instincts, and that some parts of our picture, continuous time, firm locality, the idea that properties exist independent of context, were training wheels we needed for a while. Either way, the honest path refuses to sand down the roughness too soon. The strange results deserve to be faced as they are, without wrapping them in easy stories. A photon can take paths that interfere with themselves. Two distant detectors can record outcomes that fit together too closely for classical comfort. Delayed choices can rearrange which patterns we find, in ways that look as if later decisions cast a soft light on earlier possibilities. The mathematics navigates all of this with grace. Our metaphors lag behind, panting. It helps, in a night like this, to keep the tone gentle. Think of the wave function as a hush spread over possibilities, as if a room were dimly lit and many chairs were available until you sit. Think of measurement as the moment the room chooses one arrangement and all the other chairs quietly slide back into the dark. Think of entanglement as a duet learned so perfectly that either partner, singing alone, still carries the shape of the harmony. These pictures are not the thing itself, but they are soft enough not to bruise, honest enough not to mislead. Across the community, different camps keep their lanterns trimmed. Some say everything is deterministic underneath, with hidden tracks we simply can't see. Some say the universe branches at each quantum choice, every outcome realized in a wider tapestry that seldom meets itself again. Some add a small, lawful randomness to the dynamics so that possibilities truly collapse. Others treat the wave function as information about our expectations, not a physical wave at all. Each saves certain intuitions and spends others, like travelers packing differently for the same long road. No single pack has yet proven lightest and warmest at once. It would be easy to turn this into unease, but there's a kinder reading. The absence of a final story is not a failure. It is a live edge where discovery grows. Meanwhile, the practical trust holds. The chips compute, the lasers lock, the clocks keep time so precisely that satellites guide you home. The everyday world remains steady. The small world remains lyrical, elusive, and exacting. Between them stretches the question that makes the night feel fruitful rather than empty. By what soft mechanism does the shimmer become the solid? The possible narrow into the particular, the many resolve into the one. Listen long enough, and the paradoxes stop ringing like alarms. They begin to sound like invitations, gentle, insistent knocks on the door of what we think we know. Somewhere beyond that door waits a clearer view, perhaps a deeper theory that holds quantum rules the way relativity once held Newton's, or perhaps a language more faithful to what has always been there. Until that view arrives, there's a quiet comfort in resting with the strangeness instead of pushing it away. Hold it lightly, the way you'd hold a snow globe after the flakes have settled, aware that one soft motion could stir them again, pleased that the stillness and motion coexist, that the scene is both calm and alive. Keep the light low when the metaphor is gentle. Picture a thin veil hanging over a stage. You can sense movement behind it, but the shapes only come into focus when the scene has played out. That's the feeling many physicists describe when they speak of a certain family of experiments, delayed choice quantum erasers. They're close relatives of the famous double-slit story, but with an extra twist that tugs softly on our sense of before and after. Start with a gentle setup. Single photons, little packets of light, are sent one by one toward a device that offers two possible routes, like twin paths through a garden, path A and path B. When no one tries to learn which path is taken, the photon behaves as if it glides through both ways at once, a superposition that lets the two routes talk to each other. Over many photons, this quiet conversation writes an interference pattern, bright and dim stripes, a wave-like signature drawn on the final screen. Change only one thing: arrange the apparatus so that, in principle, there is information available about which path a given photon used. No need for a human to peek at it. Merely making path knowledge possible is enough. The interference vanishes. The pattern becomes simple and grainy, as if each photon chose a single route, like a tiny marble. It's the availability of which path information that matters, not a clumsy poke from the detector. The world seems to decide differently depending on whether the story of which way could be told. Now the twist. In the quantum eraser style of experiment, the apparatus is built so that the fate of that path information, kept or erased, can be decided after the photon has already struck the screen. You let the photon travel, let it leave its tiny mark, and only later do you set the knobs that determine whether the which path story survives or is dissolved into ambiguity. The future choice concerns the bookkeeping attached to that photon's journey. The spot on the screen is already there. What shows up is not a moving of dots, not a rearrangement of the past the way a film editor might splice frames. Each individual mark on the screen stays where it landed. The strangeness appears when the full record is sorted into groups according to the later choice about path information. Take all the events whose path knowledge was effectively erased. Those accumulate into an interference pattern. Take the events whose path knowledge was preserved. Those show no interference. The past measurement and the later decision are braided together in the statistics, like two melodies that only reveal their harmony when overlaid. There is no way to use this to whisper messages backward in time. Stand at the screen alone, watching the marks appear one by one, and you see only a blur without the crisp stripes. The patterns emerge only after the data are paired with the later records that say, this photon's path info survived, or this photon's path info was erased. The correlation is discovered in hindsight. Still, something in our intuitions twinges. How can a later bookkeeping choice be entangled with the earlier wave-like or particle-like character? Some find it calming to speak in the language of the wave function, the mathematical hush that spreads possibilities across the whole apparatus. In that picture, the photon is not a separate traveler with a finished story once it strikes the screen. The entire arrangement, paths, detectors, screens, and even the devices that will later decide whether to keep or erase information forms one quantum whole. The wave function stretches over it all, assigning weights to possible outcomes across the full scene. Only when the full set of relevant interactions has happened does the story settle into a single narrative we can retell. The past we reconstruct is the one consistent with all the facts, early and late. Others suggest a softer adjustment to our sense of time. We often imagine events as beads on a string, each bead fixed as soon as it slides past our fingers. Quantum processes can behave more like a loom, where threads from earlier and threads from later meet to make a pattern at once. Before the tapestry is complete, asking whether a specific stitch belongs to this figure or that can be a premature question. What feels like a definite history might instead be a sketch that gets inked in as more of the picture is revealed. There are more daring readings, too, carefully argued by serious people, that flirt with the idea of retrocausality, that a complete account of a quantum event may need boundary conditions from both ends, past and future, without allowing the paradoxes of changing history or sending secret notes to yesterday. In these models, influence is not a courier running backward. It is more like a constraint that spans the whole timeline at once, determining the shape of outcomes in a way that only looks peculiar if we insist on building the story strictly left to right. Each view saves some comforts and spends others. Treat the wave function as a real physical field, and you gain a single, continuous storyteller at the cost of allowing reality to be broadly spread until the last moment. Treat the wave function as information about our expectations, and you preserve a tighter grip on what is, but you must explain why the book of expectations is so tightly coupled to what detectors eventually say. Embrace branching worlds, and you keep strict causality inside each branch, while paying the price of an ever-widening forest of outcomes. Add a lawful collapse, and you reclaim single results with a physical mechanism, while taking on new dynamics that have to play nicely with all known experiments. Tip your hat to retrocausal constraints, and you keep locality in the present while agreeing to a global dance that ties earlier and later together. Under the lamp's warm circle, it helps to keep the imagery kind. Think of witch path information as footprints on fresh snow. If the footprints remain, the landscape remembers a route, and the interference vanishes. If a gentle snowfall erases them, the field returns to a smooth surface where waves can overlap. The delayed choice trick is like deciding whether to sweep those prints after the traveler has already reached the porch. You don't change where the traveler arrived. You change what story the snow can support when you read it back. This gentle distinction protects causality from melodrama. The late choice never edits the earlier screen the way a novelist edits a paragraph. It edits the ledger that decides how to group the earlier dots into a pattern, and only that grouping reveals the wave stripes or their absence. The present remains free of usable signals from the future. The future remains unable to rewrite a finished diary entry. Yet, the diary and the ledger turn out to be parts of the same book. For many, this is the experiment that keeps the room quiet long after the discussion ends. It strokes the grain of three ideas at once. That information is not a casual accessory, but a structural part of how outcomes manifest. That the border between observer and observed is porous, more like a shoreline than a wall. And that our everyday grammar of time, first this, then that, may not be the grammar the quantum world prefers when it whispers to itself. The unease you might feel is reasonable. We are used to histories that are baked and cool. Here, the recipe seems to require the oven to consider the serving plate too. But notice what does not waver. No contradictions in the records. No opportunities to cheat cause and effect. No way to send a wink across yesterday. Only a carefully structured dependence that shows itself when the whole experiment is read as one sentence instead of chopped into clauses. Meanwhile, the practical side stays astonishingly firm. Physicists can predict the statistics of each grouping with painful accuracy, and the apparatus behaves with obedient consistency. The surprise lives not in the numbers, but in the picture. We want the photon to be a little bullet whose story is finished once it hits the target. The experiments keep reminding us that this is too narrow. The event is not just the dot on the screen. It is the dot plus the fate of the information that could have been, or was gently erased. If the mind wants a final moral before the light dims, it might be this: what we call a result in the quantum world is a relationship, not a solitary fact. It is a match between possibilities and the questions we ask, a truce between what could have happened and the way we chose to let the story be told. In delayed choice eraser experiments, that truce is negotiated across the full span of the setup, earlier and later, both invited to the table until the narrative settles. No drama, no time travel, just a universe that insists the whole context matters. Hold that thought the way you cradle a snow globe once the flakes begin to settle. The scene is steady for now, yet you know a gentle tap could redraw the pattern. The quiet is real, the shapes are real, and knowing they lean on one another doesn't make them less so. It folds them into a larger, softer order, where the veil isn't a barrier but a reminder to watch with care, to notice how the whole depends on how and when we look. Seen in that softer light, measurement stops feeling like a single knock on the world and becomes a slow, careful stroke of a pen, the last line deciding what the earlier lines were trying to say. In delayed choice, quantum eraser setups, even the mere possibility of learning which path a particle took, arranged after the fact, gently reshapes the pattern we read before. The border between wave-like and particle-like doesn't lock at the fork. It waits, suspended, until all the choices about information have come to rest. By habit, we picture the past as a stone already settled on the riverbed. The present can feel its weight, but the stone ignores whispers from downstream. That comforting picture is the backbone of causality, and exactly the place these experiments ask us, softly, to look again. Down in the quantum small, the experiments suggest the letter of the past may be sealed only when the reply from the near future has slipped inside the same envelope. Some people find that thought soothing, a hint that reality is more delicately connected than we guessed. Others feel a tug of unease, as if the tidy arrow of time loses its crisp outline under the microscope. Either way, the data keep their rhythm, repeated, steady, faithful to the theory's predictions. The trouble has never lived in the mathematics it knows the root, but in our attempt to translate the root into a story our daylight instincts can live with. Each translation tries, and each one snags. Perhaps the world is stitched together by a timeless wave function that spans the whole scene. Perhaps what is real waits for the question to be asked. Perhaps there is a soft, statistical echo that seems to reach backward without letting anyone rewrite a diary page. This is the flavor of paradox here, not a contradiction that kills the theory, but a circle of options that each bends our intuitions somewhere uncomfortable. The universe appears to be asking us to loosen our rulers for time, causality, and reality, and we haven't yet learned the gentlest way to do that. From the arrow of time, the thread drifts towards something even more basic, the idea that what happened is the same for everyone who looks. A quiet fable called Wigner's Friend puts the question simply: if two observers consider the same quantum system, must they agree about what occurred? In the everyday world, the answer feels obvious. A shared reality should yield shared reports. Quantum theory answers with a pause. Imagine a sealed laboratory, quiet as a winter room. Inside sits a tiny system, a particle, prepared in a superposition of two possibilities. Call them up and down, just to have names. Before any measurement, the particle holds both notes at once. In the room is a scientist, Wigner's friend, who performs a measurement and records a definite result. Suppose their apparatus clicks up. For the friend, the haze has cleared, the superposition has collapsed, reality, in that little room, has chosen. So far, this is ordinary quantum housekeeping. Now, step outside. Wigner waits beyond the door, untouched by whatever happened within. What is the state of the world from his vantage point? Quantum bookkeeping says that without interaction, the total description remains a superposition. And the total now includes the friend, because the act of measuring entangles them with the particle. The system is no longer just the particle. It is the particle plus the friend's recorded memory, woven into a single chord. From Wigner's view, that chord contains two harmonies at once. A branch where the friend saw up, and a branch where the friend saw down. From the friend's view, the event is settled and singular. Both stories are allowed by quantum rules, and yet they disagree about what has already taken place. The mind reaches for a rescue. Perhaps Wigner simply lacks the information, though an objective fact sits inside the room, waiting to be read. Quantum theory declines that comfort. In this formalism, until Wigner interacts, his description is not unknown, but definite. It is genuinely a superposition that keeps both possibilities live in his account, right up to the moment he measures. For many years, this lived as a thought experiment, argued over like a chess problem by lamplight. We can't place conscious experience itself into superposition on demand, so the story stayed mostly philosophical. But even held at arm's length, the lesson it hums is enough to hush a room. What happened may not always behave like a flat wall that every observer sees the same way. It may act more like a layered pane of glass, where the image depends on the angle, and only a direct interaction forces a shared picture. Let the breath settle, and you can feel a thread linking these tales. In the delayed choice eraser, a result is not just the dot on a screen, but the relationship between that dot and the fate of path information. In Wigner's vignette, a result is the relationship between what the friend had to witness and what Wigner is still allowed to describe as a blended possibility. Both suggest that quantum reality is not a pile of standalone facts, but answers that depend subtly on how the question is stitched into the world. A soft image helps. Think of witch path information as footprints in fresh snow. If the prints remain, the field remembers a particular route and interference fades. If a quiet snowfall erases them, the surface is smooth enough for waves to overlap. The delayed choice trick is like deciding whether to sweep those tracks after the traveler has already reached the porch. You don't move the traveler's feet, you change which story the snow can credibly tell. Causality stays intact where it matters. There is no scheme for sending a nod back to yesterday, no lever for editing what is already written. What changes is the grouping, the ledger we use to read the pattern, and that ledger includes later pages. Wigner's friend shares the same music. Inside the room, the melody has resolved to a single note. Outside, until contact is made, two melodies run in parallel. Eventually, the door opens, instruments meet, and a common track is printed. Before that moment, each listener holds a different layer of the same song. The world is not careless here, it is context sensitive. The reel it gives you is the reel that fits the frame you and it have built together. None of this forces us to believe reality is flimsy or fickle. It asks us to relax the habit of treating reality as one photograph nailed forever to the wall, and to consider that it may be a multi-pane window, whose layers align when perspectives touch through an actual exchange. Causality, the quiet structure that steadies the day, doesn't shatter. It is set into a finer frame where information that could exist becomes part of how events are braided. No one sends a postcard to last week. Instead, when enough pieces are brought together, the hidden pattern wave or particle, single value or blend, shows itself like a motif emerging under a weaver's hands. Around questions like these, different lights are kept burning. Some treat the wave function as a real, spread-out field that patiently includes devices and observers in one continuous story, settling only at the end. Some treat it as a ledger of expectations, keeping the world firmer, but then explaining why the ledger tracks the detector's click so perfectly. Some imagine many branches, trading a single world for sharp causality inside each branch. Some add a lawful, physical collapse to sew one outcome into the fabric. Each keeps a piece of intuition warm and lets another float a little in the dark. Place a hand over your heartbeat and notice what still holds. The mathematics steers with uncanny precision. The experiments keep time, steady and repeatable. If there's any unease, it gathers in the way we tell the story. How do we name a world where what has happened can wait to become fully shared? As ever, answers arrive slowly, nudged by paradoxes that refuse to settle, by the patience to treat a crack not as a flaw, but as a place where light slips in. For tonight, it's enough to see that the past and the present, the person inside the room and the one outside the door, the dot on the screen and the note in the logbook, each is a thread. Together they weave one cloth. It isn't fragile. It simply asks to be read at its own pace, slow, even revealing its pattern only when the last strand is gently laid. Follow those threads into the lab, and you find a careful rehearsal of that very question. In recent years, physicists have staged the Wigner's Friend drama, with stand-ins well-prepared quantum systems cast as observers. In 2019, a team reported a version where multiple observer-like systems measured entangled particles and wrote their notes into the quantum state itself. The setup let two observers examine the same underlying event and, under the right conditions, record outcomes that refuse to merge into a single shared story. No one blundered, the devices were sharp, and the statistics clean. Taken at face value, quantum mechanics calmly allowed distinct observers to obtain incompatible yet individually correct records, as if different hands were tracing true lines on the same cloth from different angles. That's a quiet earthquake. In the classical mood, there is one ledger of facts. If two people disagree, at least one is mistaken or uninformed. Here, by contrast, observer A can record one truth and observer B another, and each account is internally sound within its own frame. It hints that reality itself, at least at the quantum edge, may be observer-dependent, not just our knowledge of it. Different interpretive lanterns cast different kinds of light on that hint. The many-world story proposes that each measurement gently splits the tapestry, sending every possible outcome into its own branch. Inside the lab, the friend becomes two versions, one who saw up, one who saw down. Outside, Wigner's description still includes both. When Wigner finally measures, he divides two, each version finding itself with the matching friend. Everyone is right, but each is right in a different branch, and no one holds the complete album. A more traditional lamp, the Copenhagen style, keeps measurement causes collapse as a rule of thumb, and treats the observer as something special, hovering just outside the quantum book. The math works, but the borders blur. What exactly counts as an observer? And why does that role have privileges? If the friend is enough observer to collapse the state, then the outcome inside the room is settled. If not, Wigner's outside view keeps the friend in a superposition, and collapse waits. The story functions, but it leaves a soft, undefined halo around the word observer. Relational quantum mechanics takes a different breath. It says every quantum state is a description relative to someone. There is no final, God's eye account, only statements like, the friend saw up relative to the friend, and Wigner describes the friend plus particle in superposition relative to Wigner. Each description is valid in its own grammar, and there is no deeper, perspective-free layer beneath them. Reality, in this view, is not a single wall but a set of interlocking frames that agree only when they physically interact. Each way of seeing rescues something and spends something. Many worlds preserves strict local causality within each branch, but pays with a vast forest of parallel outcomes. Copenhagen preserves a single world, but pays with a fuzzy line between observer and instrument. The relational view preserves consistency without collapse, but pays with the loss of any notion of an observer-independent state. The cost is real, because what's at stake is dear, a singular reality, a clear demarcation between measured and measurer, a shared book of facts. The unsettling part is not the mathematics. The theory predicts the conflicting records, and the lab agrees. The unsettling part is what those records ask us to relinquish. We are used to one world, one set of facts, one truth that would settle any dispute if only we could collect enough information. Wigner's friend suggests that enough information might not exist in a way that merges every viewpoint. Two observers, each with complete local access, may still disagree, neither lying, neither mistaken, because each lives in a frame where the story closes differently. In ordinary life, the difference is drowned by scale and noise. The macroscopic world averages over countless microscopic details. Quantum possibilities wash together into a single, dependable tide. Coffee is spilled or not. The sun rises. Traffic lights switch on schedule. Classical physics is a grand approximation that our senses inhabit with ease. Yet the thought that each observer might, in principle, occupy a slightly different slice of the full quantum state lingers like a faint scent, usually invisible, sometimes decisive. These ideas touch the great, open questions. The measurement problem asks what, if anything, forces a wave function to narrow from many possibilities to one outcome. If different observers can witness different narrowings, or if narrowing is always relative, then collapse is not a single global event. It becomes something subtler, a stitching together of relational facts. The question of consciousness sits nearby. If observation helps decide which version of events becomes real for you, does awareness do any special part of that work? Or is it just along for the ride, while physical interactions write the record? Eugene Wigner, late in life, leaned toward giving consciousness a privileged role, suggesting that collapse occurs where experience occurs. Many physicists step back from that line. It feels like importing philosophy, where physics prefers machinery. Still, Wigner's friend leaves the door ajar. The boundary between quantum fuzz and classical firmness appears to depend on who or what is doing the counting. None of this is hand-waving. Laboratories can now set up experiments in which different parts of a single apparatus encode different, incompatible realities. The devices are not confused. they are entangled in ways that make a single, globally consistent story impossible without specifying a vantage point. The theory anticipates exactly this behavior. Feature, not bug. And yet a strange feature. It calls into question what we mean by objectivity and truth when the smallest pieces of the world are involved. A helpful picture is a kaleidoscope held in steady hands. One twist, many patterns, each crisp, none the whole scene. Observers are like the mirrors inside, arranged so that a single set of colored beads can make several legitimate symmetries. No single symmetry is the truth above all others, and the kaleidoscope never yields the mythical, complete image because there isn't one to yield. There are only patterns that become definite relative to how the mirrors are set. This matters beyond midnight musing. As quantum technologies mature, computers that choreograph entanglement, networks that route quantum keys, sensors that listen with atom-level delicacy. The question of what reality looks like from the machine's point of view becomes practical. When two quantum nodes compare notes, what counts as the note? What does it mean to reconcile records that can be incompatible until the right interaction occurs? Engineering leans on these answers. Synchronization, error correction, and security all depend on how information becomes and remains real. The paradox itself remains open like a book with several bookmarks. Some physicists favor branches, some favor collapses, some favor relations. None has won the room. What gathers agreement is gentler and more important. Wigner's friend reveals that observation, measurement, and reality weave together in a way more mysterious and more structured than our inherited language suggests. Quantum mechanics keeps delivering numbers that match the world to absurd precision, but the picture those numbers sketch resists settling into one comfortable frame. A way to rest with it. Treat facts as agreements reached by systems that have touched. Before the touch, descriptions can differ without either being wrong. After the touch, the descriptions lock together and a shared story solidifies. In the human scale, touches are constant and sprawling, so the stories align. In the quantum hush, touches are selective and small, so stories can diverge until the moment of meeting. From that angle, objectivity is not a pre-existing marble on a pedestal. It is a consensus that forms when the conditions for sharing are met. Lean into the softness of that idea, and it becomes less frightening. It does not say there is no world, only that the world reveals itself in relations, not in solitary declarations. It does not say truth is optional, only that truth is tied to context in the small and becomes context independent in the large. It does not say consciousness conjures outcomes from nothing, only that what you can rightly call real for you depends on how you and the things you interact with are woven into the scene. So the friend in the room and the physicist outside can both be right and yet not be speaking about one identical tapestry until their worlds touch. The mathematics holds their stories gently apart. The experiment confirms the gap. The interpretations offer different bridges. Whether we cross by splitting paths, by drawing a special line for measurement, or by accepting that all descriptions are relative, the landscape remains the same. A universe that keeps its promises in numbers and keeps its mysteries in meaning. And perhaps that is the consolation. The dependable glow of devices, the timing of clocks, the reliability of chemistry, these are the lullabies sung by the predictive power of the theory. The rest, the feel of reality as singular or layered, objective or relational, remains a question you can set on the nightstand without forcing an answer. When the room is quiet again, The kaleidoscope waits where you left it. Turn it slightly, and the pattern changes, still true, still precise, still drawn from the same beads, reminding you that certainty in physics is often a certainty about patterns, not about the one picture behind them all. When the earlier puzzles have softened the edges of certainty, it's natural to let the mind rest on time itself and ask whether the future ever leans back, light as a hand on a shoulder, to guide the past. The word for that is retrocausality. It sounds like a ticket to science fiction, but the mathematics of quantum theory is friendlier to the idea than everyday habits are. The core equations don't wear a preferred arrow. They work the same way whether you read them forward or read them backward, like a melody that makes sense no matter which end of the piano you start from. Our lives are written left to right, causes first, effects after, yet experiments keep nudging us to consider that the small world doesn't mind a story whose meaning is fixed only when both the first and last lines are on the page. That feeling took on shape in the delayed choice family of setups, where a gentle decision made late seems to sort earlier events into different patterns. Nothing jumps around. No dot on a screen relocates. What changes is the story the dots are able to tell once you include the later facts in the ledger. A conservative way to read this is to say the past was always fine, and we simply learned how to group it. A bolder reading is to say that the past at the quantum scale wears a softness until the full context, earlier and later, settles. One of the cleanest languages for that bolder reading is called the two-state vector formalism. Ordinary quantum talk uses a single wave function, a spread of possibilities rolling forward from some initial condition. The two-state picture adds a partner, a wave function that rolls backward from a later condition. The system, in this telling, is described by both at once, the past leaning forward, the future leaning back, and what you observe is the handshake where the two meet. If the single wave function is like tracing a river from its spring toward the sea, the second is like starting at the ocean and drawing the river back to its source. For a classical stream, the two descriptions are redundant. For quantum water, the flow at a given bend can depend on both the upstream and the downstream boundary. Collapse, in this view, is not a sudden thunderclap. It's the quiet consequence of fixing the edges of the picture. Once the starting frame and ending frame are set, the middle has little room to wriggle. That shift steals much of the drama from delayed choice tales. If the later boundary is part of the definition, nobody has to act surprised that earlier statistics line up with later settings. The surprise is in us, not in the math. We are used to causes wearing boots and walking in one direction, while here the causes wear ballet shoes and meet in the middle. The comfort it offers is real, no mysterious collapse, no privileged instant, just a smooth stitching of constraints from both sides. The cost is real too. Once you let future conditions help define present behavior, questions about free will pull up a chair. Follow that thread, and you may find yourself in the block universe mood, where all of space-time is a single sculpture, past, present, and future as different neighborhoods of one four-dimensional city. In such a city, your choices are streets that already exist, and making a choice is the act of discovering which street your address inhabits. Some people find the permanence of that picture restful, like knowing the map is printed in full. Others find it too still, as if agency were only the feeling of riding rails. Strictly speaking, retrocausality doesn't force this sculpture on you, but the two ideas sit comfortably on the same bench. If time is more like space than we thought, it is less surprising that influences can be described from both temporal directions. It helps to keep clear what these ideas do not offer. There is no recipe here for sending notes to last week or editing yesterday's diary. The paradoxes that make good movies, killing grandfathers, rescuing ships before they sink, belong to a different shelf. In quantum retrocausality, as physicists mean it, no controllable signal crawls backward to change a settled fact. What you get instead is a subtler claim. To tell the full causal story of a tiny event, you may need to cite both its ancestry and its descendants. The event is hemmed in by conditions at both ends, the way a maze is easier to solve when you know the entrance and the exit. The path isn't rewritten after the fact, it is picked out by both facts at once. Seen in that light, entanglement starts to look less like a scandal and more like choreography. Two particles set out from a common preparation. Their properties are correlated in a way that makes distant comparisons line up uncannily well. Read naively. One measurement seems to reach across space faster than light to nudge the other. Read with boundary conditions in mind. The pair is a single pattern stretched across two places, and the instantaneous match is the natural fit of both measurements to the same global constraints. No message travels. No rule of relativity is bruised. The harmony is written in the joint setup, not piped from one site to the other in secret. Even without committing to retrocausality, the mere exercise of entertaining it softens the paradoxes. The delayed choice experiments lose their whiff of magic. The choice made late becomes part of the definition of the event, not a wand waved over a finished past. The two-state description replaces a jump with a glide. The questions it raises are worthwhile ones. How do boundary conditions emerge in open, messy environments? How do macroscopic facts, thermometers, calendars, shared records, rise out of microscopic constraints that care about both ends? If a worry remains, it's the old friend with a new coat. Where does freedom live if the future leans back? One way to rest with that is to notice that constraint is not compulsion. A sonnet's rhyme scheme limits the words you can choose. It does not write the poem. Boundary conditions narrow the viable paths through the maze. Within those paths, the details still sing. In practice, the future that matters as a boundary is not your personal decision tomorrow morning about toast. It is the full web of interactions that will eventually count as facts in the shared world. Between now and then lies a spacious room where choices and chances wander, and nothing in the formalism gives you a steering wheel for yesterday. Another way to rest is to remember the scale at which these subtleties carry weight. The night sky of daily life is classical for excellent reasons. Decoherence, those countless gentle entanglements with the environment, washes quantum softness into crisp, macroscopic facts. Arrows of time emerge from thermodynamic bookkeeping. Memories store in one direction. Eggs do not unscramble once the pan is hot. Retrocausal talk lives in the hush beneath that bustle, where carefully shielded systems can preserve the delicacy needed for both-ended descriptions to make sense. Step out into sunlight, and the two-ended melody is drowned by the lawnmowers and birds. Still, the melody is there, and learning to hear it changes how the rest of the symphony feels. You stop insisting that cause must always march. You allow that sometimes it can pirouette. You stop treating the past as a brick wall and start treating it as a fresco whose colors fix as the plaster dries. You stop demanding a collapse and start accepting a meeting, a rendezvous of constraints that leaves a single trace where many paths could have been. A few careful metaphors can help the mind settle. Picture a crossword with both the clues and the filled-in letters arriving from different corners. A letter written later can make sense of an earlier square without erasing the ink. It resolves the ambiguity that was always there. Or picture a bridge built from both banks at once. The shape near the middle is determined by how the arches are launched from either side, even before the keystone slides into place. Nothing supernatural happens when the final stone is set. The structure becomes what it was always headed to be, given both beginnings. What matters, at the end of a quiet evening, is not to pick a dogma, but to see the range of gentle possibilities the data allow. You can keep the forward-only story and take delayed choice as clever conditioning in disguise. You can adopt the two-state view and let future facts help draft the present. You can stand in the block universe and study the sculpture. You can remain agnostic and simply note that the equations don't protest if we write them from both ends. Across these options, the shared moral is simple. Context matters for tiny things in a way our daylight grammar doesn't capture. And sometimes context includes what hasn't happened yet in our personal time. Hold that moral lightly. Let it be a soft weight in the palm, not a burden. The clocks will still keep time. The kettle will still sing. Down in the small places, though, a photon may wait for the story to finish before choosing which character it was, and a pair of particles may act like a single line drawn across space. If the future has any voice in those lines, it is not a shout. It is a whisper that completes a sentence already half true, and it leaves the world no less trustworthy, only more intricately woven than we first imagined. Letting the future have a quiet say makes entanglement stop looking like a secret telegram racing between partners. The match between two distant measurements can be read as both of them fitting the same future boundary, not one nudging the other across space. In that retrocausal picture, measuring here doesn't send a wink over there. Both results land consistently because the whole story earlier and later has to agree with itself. Locality, the simple idea that influences travel only through their immediate surroundings, stays intact. When you and I measure our separated particles, neither of us reaches across the gap. Instead, our records rhyme because they both satisfy the same global constraint that lives at the far end of the experiment. The universe, in this telling, is self-consistent across time, and that self-consistency writes the correlations we observe. Not everyone is soothed by that move. Critics point out that the puzzle may not be solved so much as relocated. Instead of asking, how can two particles coordinate without a signal? We ask, how can later facts help set earlier ones? It's one strangeness traded for another. Then comes the issue of tests. If retrocausal influence never carries a controllable message into the past, and if its fingerprints show up only statistically and only after careful sorting, can we ever prove it as more than a helpful way of speaking? Physicists have proposed subtle experiments that track timing and correlations with exquisite care, looking for patterns that different models predict differently. So far, no decisive verdict has arrived. Retrocausality remains an open door in the foundations, neither slammed shut nor inviting enough to declare it the main entrance. What keeps the door from creaking closed is that retrocausality isn't a flight of fancy added on top of the math. It slips out of the math itself. The basic equations of quantum theory do not come with an arrow painted on them. They're time-symmetric, happy to be read forward or backward. When you try to translate such symmetric lines into a picture of processes, one honest picture is that events can be constrained from both ends. That suggestion brushes a larger riddle we carry from dawn to dusk. What is time? To us, time feels unlike space. You can step left or right, but you cannot stroll into yesterday. The past seems sealed, the future unpicked. Yet the fundamental laws, classical and quantum, are almost entirely indifferent to direction. Reverse a clean video of billiard balls colliding, and Newton smiles. Integrate Schrödinger's equation backward, and nothing breaks. So where does the arrow come from? The usual path points to entropy and the second law. Entropy counts how many microscopic arrangements fit the same macroscopic look. In closed systems, it tends to climb. That climb gives time a felt direction. Whole eggs become omelets, not the other way around. Footprints appear in fresh snow. They don't erase themselves. But entropy is statistical, a choir that sings only when many voices are present. At the level of a few quanta, the laws do not require an increase. The arrow, then, may be something that emerges when the world is large, open, and noisy. Down in the small and quiet, time may not pick a side at all. If that is right, retrocausality loses some of its menace. It is not that effects storm backward through history. It is that our forward-flowing intuition, trained on hot kitchens and broken eggs, does not apply cleanly in the hush of the quantum. Reasonable people disagree. Some build retrocausal models and try to show they iron wrinkles more gently than forward-only pictures. Some prefer interpretations that keep causation one way and accept non-local correlations as basic. Others suspect the whole debate is a category error, an attempt to force classical words about causes onto a world that answers in a different grammar. All can agree on this. Time in quantum mechanics refuses to behave like a single straight road. The delayed choice experiments showcase that refusal in hardware. What the strangeness means retrocausal stitching, timeless wave functions, or a new idea not yet on the table remains open. Whatever the final story, the future plays some role in how we understand the past, even if the role is only that later facts help us group earlier data correctly. Shift your attention softly from time to space and watch entanglement perform a trick with a charming name: quantum pseudo-telepathy. Telepathy it is not. No minds are read. No messages sneak between rooms. But the scores it delivers look uncanny compared with anything classical planning can achieve. Here is the shape of it. You and a friend sit in separate rooms. No communication allowed. Each of you is asked a question chosen at random from a small list, and you must answer yes or no. The rules are set so that certain pairings of answers count as a win. Beforehand, you can agree on any strategy you like. Lookup tables, mnemonics, a perfectly rehearsed plan. In the classical world, probability sets a ceiling on your success. No matter how cleverly you plan, some combinations of questions will trip you up. With the best classical strategy, you might win very often, but never always, and never beyond a strict limit that the math draws like a clean horizon. Now give each of you one particle from an entangled pair. When a question arrives, you choose a corresponding measurement to perform on your particle and translate the outcome into yes or no. Individually, each outcome looks like a fair coin. Together, the outcomes are correlated in a pattern that slips past the classical ceiling. In some games, the win rate presses right up against certainty for the allowed questions. In others, it exceeds the sharpest classical bound by a clear, measurable gap that no amount of prearranged charts can bridge. The nickname sticks because, on paper, it looks as if you and your friend are sharing thoughts. In truth, you are sharing an entangled state, a duet written before the questions are drawn, and quantum mechanics conducts the rhythm. The beauty is in what does not happen. No signal races between the rooms. Relativity stays unruffled. Each room's data, taken alone, is random. Only when the two answer sheets meet does the hidden harmony appear. If you like retrocausality, you can tell this story without any hint of faster-than-light hush. Both measurements sit inside one web of constraints that includes their shared past and their eventual readout, so they fit together without sending secret notes. If you dislike retrocausality, you can keep the standard account. Non-local quantum correlations are simply part of the furniture. Either way, the game works and the world keeps its speed limit. It's fair to ask whether any of these pictures will ever feel as clean as flipping a light switch. They may not need to. The numbers are clean, the devices obey. What remains is to choose the lullaby that lets you rest, a universe that knits events with threads running both directions in time, or a universe that keeps causes marching forward while allowing correlations that outstrip every classical plan. Tonight, it is enough to hold both gently. The rooms stay quiet, the chalk still records true, and somewhere, two tiny coins tossed in silence keep landing with a pattern that only makes sense when the pages are turned together. Imagine that before the doors close, you and a friend each pocket one particle from a pair prepared in a special way. They're entangled, described not by two separate stories, but by a single quantum state spread over both. It's less like two coins and more like one melody played on two instruments in different rooms. When the game begins, a question arrives. You answer by choosing how to measure your particle. Your friend, elsewhere, does the same with theirs. No whispers pass between you. The rooms stay silent. Later, when the answer sheets meet, the pair of melodies reveal a harmony that no classical strategy can match. The win rate leaps beyond the best a prearranged playbook could ever guarantee, a result repeated in laboratories with careful timing and clean statistics. This is the heart of quantum pseudo-telepathy. It looks like mind reading, but nothing travels between minds. Each local list of outcomes, viewed alone, is as random as rain. The power hides in the joint pattern, the way two columns of numbers lock together when finally compared. Entanglement supplies the duet. Measurement turns notes into answers. A favorite illustration is the magic square game. Picture a 3x3 grid to be filled with 1 second and 1 second. The rules ask that each of 3 rows multiply to +1, while each of 3 columns multiplies to 1. Classical logic can push you far, but not all the way. Any table you design will fail somewhere. The constraints simply don't coexist in a single classical assignment. Share entanglement instead, and you and your partner can adopt measurement rules that map outcomes to entries, row by row and column by column. The quantum strategy hits every constraint every time. What the classical chart forbids, the entangled duet accomplishes without a single whispered hint. There is a cousin with 3 players, the GHZ game, named for Greenberger, Horn, and Zeilinger. 3 friends sit apart. Each receives one of 2 possible questions and must reply with yes or no, or equivalently, +1 or 1, so that certain parity conditions are met together. Classical plans run into hard ceilings, no matter how clever the pre-game pact. Some question combinations force a loss. Share a 3-way entangled state, and the ceiling lifts to certainty. The answers, locally coin flip random, combine into a perfect chorus when placed side by side. What's really happening is quieter than any talk of secret channels. Entanglement means the pair or trio is not a set of independent objects that carry pre-written properties. Before you look, there isn't a hidden label inside each particle saying, "This is up," or "That is down," for every measurement you might choose. The properties are context-tied, and measuring here trims the menu of what can appear there in a way the joint state has already encoded. The crucial restraint is that no message rides on that trimming. If you inspect only your data, you see fair coin randomness. Only after ordinary, slower-than-light comparison do the correlations bloom. That's why the effect earns pseudo. It fakes telepathy's outcomes without granting telepathy's powers. This point has edges sharp enough to carve. In the 1960 seconds, John Bell translated the EPR, Worry, Einstein, Podolsky, and Rosen's famous challenge into inequalities that any local realistic theory must obey. Local means influences travel no faster than light and only through nearby touches. Realistic means measurement uncovers pre-existing values rather than bringing them into being. Quantum mechanics predicts violations of those inequalities. Experiments have confirmed the violations again and again, closing loopholes with stubborn care. Nature's correlations outrun the tightest limits of any world where properties exist ahead of time and nothing non-local ever sneaks in. The road forks, and each fork asks for a familiar comfort in trade. You can relax locality and keep a single set of definite properties, allowing that entangled systems share a non-local bond that space cannot neatly separate, though still not one you can use to signal. You can relax realism and say properties don't sit there waiting. They crystallize in the act of measurement, with the joint state guiding which crystals can form together. You can keep both locality and quantum predictions by giving up counterfactual definiteness, the idea that unasked questions nevertheless had definite answers, accepting that what would have happened is not a thing the world is obliged to carry. Each choice redraws a line we thought was permanent. Einstein called the whole business spooky action at a distance, and trusted that hidden variables, missing details would someday tame the spook. Bell showed that any such details, if they stay local, cannot do the job. The experiments sided with Bell. The spook remained, but it wore a sensible uniform, strong, lawful correlations, without faster-than-light messages, and without pre-assigned answer keys. Pseudo-telepathy games make this visceral. Two people, no talking, perfect scores. The only way to square that circle classically would be a hidden link. The quantum world keeps the scores while forbidding the link. If you're leaning toward the retro-causal mood from earlier, these games can be told without giving up locality. The coordination comes from a global consistency across time. Both sets of answers fit the same boundary conditions. What settings were chosen, what records were eventually compared so they mesh without a courier. If you prefer to keep time strictly forward, you can still keep locality and let go of counterfactuals, or keep realism and accept non-locality as a fundamental feature that cannot be harnessed for signaling. Many worlds offers another lullaby, the entangled state. The devices and the observers form one big wave that branches. Each branch contains definite, matching answers for each player, and no branch needs to explain how it learned about another. Branches do not talk. They merely coexist as different pages of the same book. What these perspectives share is a redefinition of what it means for distant things to be one system. At the quantum scale, oneness is not about proximity, but about preparation, how the state was stitched together at the start. Separate the parts by miles, and the stitching remains. What you can say about one depends on how you choose to ask about the other, not because your choice reaches out through space, but because both answers belong to a single pattern that only reveals itself when the pages are read together. There's humility in this. The world is not a warehouse of independent items labeled in advance. It is more like a fabric, where some threads are so tightly woven that pulling on one changes the weave available to another, even far away. The change is not a tug you can feel. It is the quiet fact that the cloth's pattern limits what can appear where. Pseudo-telepathy puts your fingers on that fabric. You and your friend, working in silence, still produce a pattern that a classical loom cannot weave. It circles back to what counts as a fact. Alone in your room, your results are facts for you. A list of +1 second and 1 second, nothing more. Only when facts meet, when records are brought together, does the richer structure show. Objectivity, in this light, is the agreement formed where worlds touch. At everyday scales, touches are constant, so agreements are universal and causality feels like a straight road. In the quantum hush, touches can be sparse, and agreements can depend on how and when we choose to meet. The marvel is that within that hush, the rules are still as strict as a metronome. No cheating, no whispers, no messages faster than light, and yet, with entanglement as the score, the duet wins every time the game allows. In one gentle telling, the branching picture keeps everything tidy. When measurements happen, the whole scene, the particles, the devices, even the observers, unfurls into parallel strands. Each strand carries a definite outcome, and inside any one strand, the correlations look perfect because the story there is self-consistent from end to end. Nothing has to sprint across space to coordinate with anything else. The entire tapestry is one quantum state, evolving deterministically, and what looks like coordination at a distance is simply the way a single piece of music sounds when you listen from inside one harmony. Another telling is Bohmian mechanics, where particles keep their feet on the ground. Each has a definite position at every moment, but the path it takes is guided by a pilot wave, the wave function that is genuinely non-local. The pilot wave stretches across space and ties distant partners together instantly, steering them in ways that create the observed correlations. Realism is kept. The particles always are somewhere, and locality is surrendered explicitly. The guidance can be global. The tone is calm, but the web is real. A third telling is relational quantum mechanics. Here, quantum states are never absolute. They are always given relative to some observer or system. The two players in a pseudo-telepathy game do not share one objective quantum state floating above them both. Each has a state assignment relative to their own interactions, and consistency rules ensure that when their records finally meet, the stories match along the seams. Correlations arise because the accounts are constrained to dovetail, not because a single privileged state dictates everything from nowhere. Different stories, different comforts. What does not change is the experimental heart. Entanglement produces correlations beyond classical limits. It coordinates without communication. It shows that the deep rules are non-classical in a way that shapes how systems can interact and agree. The consequences aren't just philosophical, they're practical. Quantum cryptography uses entanglement as a tripwire. Any eavesdropper who tries to peek necessarily disturbs the shared state, and the disturbance shows up as a telltale noise. Quantum computing uses entanglement as scaffolding, letting quantum bits explore structured superpositions that no array of classical bits can emulate efficiently. The correlations are not decoration, they are the architecture. Underneath the circuits and protocols, a quieter thought unfolds. Entanglement suggests the universe isn't made of isolated items that occasionally bump at the quantum level. Separate is a surface word. Two particles, two devices, two people can be parts of one extended state, still able to write matching notes even when miles lie between them. Space divides the laboratory floor plan. The deeper description ignores the wall. What looks like two things may be two faces of one quantum whole. The wave function does not stop at the door. None of this is vague hand-waving. The games are played, the inequalities are violated, the loopholes are closed, and the same strange music keeps playing. Each time we test, the universe answers with a pattern that refuses to be squeezed back into classical expectations. Coordination without messages is real, lawful, limited, and repeatable. The meaning of that fact for space and separation is still being written. Holding that in mind, the next twist lands softer. Sometimes, in the quantum world, you can even separate a thing from one of its properties. The image has a whimsical name, the quantum Cheshire cat borrowed from Alice in Wonderland, where a grin lingers after the cat has faded. In the laboratory version, the grin is a property such as spin. The cat is a particle like a neutron. The claim, carefully phrased, is that under the right conditions and with the right kind of gentle probing, the neutron can behave as if it travels along one path while its spin leaves traces along another. Spin, here, deserves a calm word. It is not a tiny sphere whirling like a top. It is a quantum degree of freedom that acts in some ways as if something were spinning, producing magnetic effects and discrete up or down responses along a chosen direction. In the usual picture, spin belongs to the particle as intimately as mass or charge. You don't expect it to wander off. The setup uses an interferometer, an instrument that splits a particle's journey into two routes and then recombines them. Send a neutron in, and it enters a superposition, not either path A or path B, but both, in phase, until an aggressive measurement forces a decision. If you slam the doors with a strong measurement to ask which path, the superposition collapses and the subtlety vanishes. The trick of the Cheshire experiment is to use weak measurements, instead gentle taps that gather a hint of information from many identically prepared runs without shattering the superposition in any single run. Weak measurements are like brushing dust with a feather rather than pressing a stamp. Each touch is too soft to resolve the picture alone. But by repeating the process many times and conditioning on a chosen final outcome, a step called post-selection, you can build up reliable statistics about where different aspects of the system tended to be. With that careful bookkeeping, experimenters can ask two questions in parallel. Where does the neutron prefer to leave its mark? And where does the neutron's spin prefer to leave a magnetic signature? The surprising answer that emerges is a split personality. The particle's position signal leans toward one arm of the interferometer, while the spin signal leans toward the other. Clarity matters here. Nothing is literally torn in two. There is no disembodied spin drifting down a hallway while a neutron sulks elsewhere. The observation is subtler. Weak values extracted from the data say, had you looked strongly for the particle itself, you would most likely have found it along path A. Had you looked strongly for spin effects, you would most likely have found them along path B. The combined statistics behave as if position and spin were delocalized across different routes during the superposed journey. To a classical ear, this is outrageous. Properties belong to their owners. A ball has its color, A car has its weight. You cannot send the ball left and its redness right. Quantum mechanics, forever patient, replies that the owner is a quantum state rather than a tiny solid bead, and states can distribute their traits in ways the classical picture forbids. Position, spin, energy, momentum, these are not rivets hammered permanently into a chassis. They are different faces of a single wave function that can spread, interfere, and, under gentle interrogation, hint at patterns that look like temporary separations. The method's gentleness is essential. Ask too hard, perform a strong, path-revealing measurement, and the effect collapses. The neutron is forced into one path or the other, and the spin comes bundled along. Ask softly and in aggregate, and you get to keep the superposition while still reading faint clues about where different aspects reside. It is as if the cat stays in both corridors, but the smile favors one. What should you make of that smile? One school hears it as evidence that properties themselves can be delocalized features of a field-like state rather than badges pinned to a corpuscle. Another reads it as a statement about information. Weak measurements, together with pre- and post-selection, pick out a sub-ensemble for which the best inference places position and spin on different arms. Either way, the moral is gentle and firm. Quantum objects are not little stones with labels. They are structured possibilities that take on unified, classical traits only when a decisive interaction knits the pieces together. If you like to connect threads, the Cheshire Cat sits comfortably alongside pseudo-telepathy and the earlier paradoxes. All of them say that what counts as where and what depends on how the question is asked and how the answers are gathered. In games, entanglement welds distant answers into patterns beyond classical reach, coordination without whispers. In delayed choice tales, later settings help decide which earlier patterns we are allowed to read context across time. In the Cheshire Cat, a softly interrogated system lets different aspects lean into different paths, context, across space, within a single traveler. None of this grants superpowers. No faster-than-light messages, no diaries rewritten, no cats literally cut in half. It does grant a more elastic sense of how identity, property, and place weave together before the world hardens into the outcomes we share. Practical minds may ask whether such delicacies matter outside dim labs. They do, if only because quantum technologies live by the same rules. Weak measurements refine precision sensing, post-selection sharpens signals, careful control of spin and path underlies neutron interferometry and quantum metrology, but the larger gift is conceptual. The Cheshire Grin invites us to relax the classical habit of thinking that things carry their properties like luggage. In the quantum hush, the luggage and the traveler can part ways for a while, not as objects, but as patterns in a single, extended state. So the picture that tucks you in tonight is wide and consistent, branching stories where everything fits within its strand, guided particles steered by a global wave, relational descriptions that only lock when records meet, entanglement that coordinates without a word, and, flickering at the edge of the beam, a cat whose smile lingers down one corridor while soft footsteps fade down the other. The world remains trustworthy, the numbers insist on it. It also remains stranger than the daylight mind expects. Between those two truths is the quiet space where science and sleep are good company, and where a little wonder is not a disturbance, but a blanket. Weak measurements make a different promise. Ask softly enough, and the superposition survives. Look with a feather, and the odd separation stays in view. Not everyone is persuaded by the quantum Cheshire cat reading, though. Skeptics point out that weak values don't straightforwardly report where the particle or its spin really are. They report something about the quantum state, about phases, amplitudes, and the subtle bookkeeping of pre- and post-selection, turning those numbers into a tale about a traveler and a wandering smile, maybe reading past the text. The math is crisp. The physics story you hang on it is the part people debate. Supporters answer that a measurement is a measurement, even when it is gentle. Weak probes still extract information from the system. They just do so without smashing the superposition. If the formalism says position-leaning evidence piles up on one arm while spin-leaning evidence piles up on the other, perhaps we should take that hint seriously instead of trimming it to fit classical furniture. The disagreement is less about the equations and more about how to translate them into pictures. Quantum mechanics is fluent in prediction and famously coy about meaning. Different readers take the same grammar and compose different poems. Either way, the lesson is steady. Quantum systems are not classical objects with labels glued on. Properties do not behave like tags that ride along in a tidy bundle. The picture of a particle as a tiny, localized bead with fixed traits is a convenience that breaks under fine inspection. Context matters. When and how you ask matters. The Cheshire cat effect sits on the same shelf as the measurement puzzle, Wigner's friend, and entanglement. Properties can be undecided until measured. Different vantage points can host different descriptions. Classical notions of here and there, this and that, are too stiff for the small world's dance. There may be uses hiding in that strangeness. Quantum information theory treats where the information lives as a design choice, and property separation tempts new architectures. If aspects of a state can be teased apart, position down one line, spin down another, perhaps there are protocols that split knowledge in a way an eavesdropper cannot fully capture. Ideas have been floated for cryptography and computation that exploit this gentler bookkeeping, where an adversary would need to intercept both the traveler and the grin to reconstruct the message. Whether these sketches mature is unknown. The result is young, and the field is careful. Still, it's another instance of quantum mechanics revealing a usable lever just where classical common sense would never have reached. The image lingers because it is beautifully wrong by classical lights, a grin without a cat. It touches the core of what makes the theory feel alien, not hand-wavy impossibility, but precise, reproducible, mathematically lawful behavior that refuses old categories. A particle should carry its properties. The properties should be where the particle is. Quantum mechanics is indifferent to should. It cares about what the formalism permits and what experiments record. And in this narrow, carefully defined sense, the grin can favor a different corridor than the cat's footsteps. That thought nudges a larger question. What is a thing exactly, if its properties can drift? Are particles cores with traits attached, or are they patterns of relations that usually travel together and sometimes do not? The theory does not deliver a final ontology on a silver tray. It gives you a toolkit that predicts outcomes and a zoo of interpretations that try to make the predictions feel at home. The meaning stays slippery, and the experiments keep being repeatable. We can draw what happens. We hesitate to say what it is. The quiet of the room deepens, and with it, the courage to look at a harsher thought experiment that many would rather keep at arm's length. This one turns the spotlight from objects to experience. Earlier puzzles tugged at time observation, space, and properties. This one steps closer to the pulse. It asks what the quantum story might mean for consciousness, survival, and the very texture of a life lived from the inside. The nickname is unsettling: quantum suicide, sometimes quantum immortality. It takes the many worlds interpretation to its most uncomfortable ledge. Here is the scaffolding, kept abstract and safe because this belongs to philosophy, not to practice. Many worlds says that when a quantum measurement with multiple possible results occurs, reality branches. Every outcome happens, each in its own strand, and the strands do not meet. You experience one outcome because you find yourself in one strand. Another version of you experiences another. In textbook examples, this means spin up here and spin down there. Strange, but manageable. The thought experiment turns the dial to a life or death scenario driven by a quantum chance. Picture a device controlled by a truly quantum coin, two outcomes, each with a 50% weight according to the theory. Tie that coin, in the barest theoretical sense, to a dangerous consequence in one outcome and a harmless consequence in the other. In many worlds, each activation produces two strands. In one, the harmless path; in the other, the fatal one. An outside observer, reading across branches, expects the ordinary statistics: half survive, half do not. From the first-person seat, the story is drawn differently, and this is the part that provokes uneasy fascination. You can only continue to have experiences in the branches where you survive. You never feel the moment of not existing in branches where the dangerous outcome occurs. There is no you there to notice it. If the device is activated once, your awareness continues only in the surviving strand. If activated twice, awareness continues only in the smaller set of strands, where both turns came up harmless. Repeat the setup in imagination, and, from the outside view, the chance of ongoing survival drops exponentially. From the strictly first-person view, experience traces only those rare strands where survival keeps happening. That bare logic is what people gesture at with quantum immortality. In a branching universe, there is always at least one strand in which you make it through, and your subjective stream can only ride strands where it is present. This is not an invitation, not an endorsement, not a path to practical longevity. From everyone else's standpoint, the overwhelming chance is that a person would be gone after very few rounds. From the God's eye summary of all branches, most versions of the experimenter do not continue. The point is conceptual, not actionable. It is also ethically and emotionally charged, and it deserves a careful border drawn around it. This is a thought experiment only. It is used by philosophers and physicists to probe what branching could mean for first-person experience, not to propose behavior in the real world. Never to minimize the reality and gravity of risk, harm, or loss. If this topic stirs distress, it is more than okay to skip it. Keep the lights gentle on yourself. Held at arm's length, the thought is still provocative. If many worlds is the right frame, does subjective continuity select for improbable survival strands? Does that selection say anything about what we should expect to observe? Most researchers say no in practice. The theory does not bless any one branch with higher measure with greater statistical weight because someone is watching from within it. And the world we share is built from the overwhelming weight of ordinary branches where ordinary statistics hold. Your experience, your loved one's experience, our collective records, all of it testifies that improbable escapes are rare, not routine. Decoherence thermodynamics, and common sense take the wheel well before philosophical curiosity could make trouble. Even so, the thought experiment tests the edges of our language. It asks where identity lives in a branching picture and what it means to talk about you across diverging strands. It forces the same question the Cheshire Cat whispers from the other side. Are objects and selves best understood as bundles of properties that can, under special rules, come apart? Or are they patterns held together by relations and records, with continuity defined by the way information flows rather than by an indivisible core? The nighttime moral, such as it is gentle. Quantum mechanics keeps drawing us toward views of reality where context matters and wholeness is larger than any single snapshot. Weak measurements hint that a particle's aspects can lean into different corridors when you look softly enough. Pseudo-telepathy shows that distant answers can fit together without a messenger. Delayed choices remind us that patterns may only sharpen when the book is closed. And many worlds, taken seriously, asks how a life feels from the inside if every possibility is realized somewhere, even when only one is realized for you and me. These are not conclusions to be swallowed whole. They are careful questions, lamplit and slow, designed to be set down on the bedside table without demanding an answer before sleep. The experiments are firm, the interpretations are provisional, the universe is patient. Between the predictability of the numbers and the pliability of the meanings lies that familiar quiet, enough truth to rest on, enough wonder to dream with. Stretch the logic to the messy places where real lives unfold and the softness sharpens. Every moment in a body is a small storm of quantum events, molecules nudging, ions tunneling, proteins folding and misfolding, neurons trading whispers of charge. Most of those flickers don't decide anything dramatic. Some might. A fluctuation could nudge a heartbeat away from trouble or into it. A bond could hold that keeps a cell steady or slip in a way that seeds harm. If the many worlds picture is the scaffolding beneath it all, then in some branches those tiny rolls of the dice lean one way and a life continues. In others, they lean the other way and a life ends. Follow the logic of quantum immortality, and the first-person story always tracks along the branches where the lights stay on. From the inside, it could feel like a series of narrow escapes, unlikely survivals that stretch belief. From the outside, it is only the arithmetic of dwindling odds. What sounds, at a glance, like a wish, an endless continuation of experience, looks different under a steadier lamp. The idea does not promise comfort, health, or company. It promises only continuity. The surviving strands, if they exist as imagined, need not be kind ones. A person could end up as the only one left in a wreck that took everyone else, or badly hurt but still conscious, or held to life by improbable balances that don't allow for rest. Nothing in the logic speaks to aging. Time keeps its count. Muscles tire, memories blur, systems fray. In the worst sketches, awareness persists into extremely old, fragile states, buoyed by strings of tiny improbabilities that keep basic functions barely working. That isn't a dream of immortality. It is a chill thought, best left as a cautionary edge to a philosophical puzzle. Even before the ethics, there's the question of coherence. Does the reasoning itself make sense? The whole picture depends on many worlds being not just elegant mathematics, but the architecture of reality, and on consciousness having a clear rule for which branch it rides. Those are large, unsettled assumptions. We do not yet know how awareness arises in brains. We do not know how to translate a branching quantum state into the continuity of a life lived from the inside. Many physicists who admire many worlds are still wary of the immortality corollary. They point to measure, the technical weight that outcomes carry. Under that accounting, the overwhelming fraction of your measure aggregates in branches where ordinary statistics win, where risky sequences end quickly. A vanishing sliver remains in the outlandish strands where survival keeps repeating. In a sober sense, you mostly die, even if a filament continues in theory. Others question the premise about awareness itself. When branches diverge, perhaps what we call I also diverges, and the version that meets an ending has the experience of ending in a way our language struggles to capture. Or perhaps consciousness demands a level of organized brain activity and integration that many hypothetical surviving branches do not actually sustain. A flicker of heartbeat with a shattered integrative network might be biology, but not experience. In that case, appeal to survival strands would not guarantee a continued point of view, only a pulse. The puzzle reaches into personal identity too. If the universe keeps sketching near copies, which one is truly you? Is there a single line threading through the fibers? Or is you a family resemblance across many strands? If all branches host conscious versions, all equally real by the rules of the theory, then saying, your experience continues only in the surviving branches, loses some bite. Experience continues in all branches as their own you. The version that lives through 20 trials is not privileged over the version that stopped at the first. Each is a center of experience within its own strand. Language strains because it was built for single rivers, not braided deltas. Quantum mechanics does not answer these human questions. It raises them with unusual sharpness. The mathematics of many worlds is a clean engine for how wave functions evolve and decohere, how environments record outcomes, how classical certainty emerges from quantum blur. It is quiet about what it feels like to be a witness inside the machine. Quiet about whether subjective continuity is even a well-posed notion in a world that keeps dividing. That silence is one reason the immortality idea lives only as a thought experiment. It remains firmly in the realm of philosophy, not practice, and it must remain there. Any discussion of devices or risk belongs to imagination, not to action. Real life is precious. Speculation is never a reason to gamble with harm. Even with the guardrails up, the thought experiment tempts because it brings the abstraction home. We are not separate from the physics we use to describe everything else. Brains are matter, following quantum rules at many levels. If many worlds were correct, then at every heartbeat there would be gentle spray into countless close cousins of the present. Most would be indistinguishable to anyone involved. Some would slowly drift apart into different choices, different friendships, different weather on a crucial day. A tiny few would diverge drastically. The idea asks what it is like to be someone inside such a spray, always anchored to one thread, while knowing there are others next to it, neighbors forever out of reach. The gentle answer is that lived experience feels like a single line, because the vast weight of branches are near copies for long stretches. Most microscopic differences wash out in warm, busy systems. The feeling of a unified self is not a mirage. It is an emergent stability, like a melody that persists even when the air vibrates with countless other sounds. The disturbing answer is that when stakes are high and the outcomes binary, many worlds forces us to confront how much of our sense of continuity depends on shared records and shared bodies, on the way information flows and settles, rather than on some indivisible essence that survives every cut, Reactions to the immortality idea are rarely neutral. For many, it rings wrong on contact, frightening, absurd, or both. That reaction is instructive. It suggests that deep intuitions about identity and awareness are being crossed by a theory that was not built to carry them. One possibility is that those intuitions are simply out of place here, habits carved by a classical world, now creaking at the quantum edge. Another is that the discomfort is diagnostic. Maybe consciousness involves features about integration, about value, about meaning, that the physics, as physics, does not and need not capture. It is okay to let that be an open window rather than a draft. There is also a practical limit that sets this thought experiment apart from the earlier quantum puzzles. Most paradoxes we have whispered through can be, and have been, tested. Delayed choices, Wigner-style scenarios with quantum stand-ins, games that display pseudo-telepathy, interferometers that hint at Cheshire grins. They involve apparatus, statistics, and public records. The immortality scenario can never be tested in that way. It hinges on first-person continuity, on what a single stream of experience would or would not encounter. And first-person experience is not the kind of thing that can be shared, replicated, and checked like a detector's output. Ethical boundaries make that absolute, and so they should. Even if they did not, any result would be unreadable to others. A survivor cannot know whether survival rode a rare branch or a lucky coin in a single world. A non-survivor has no report to give. That impossibility is not a flaw in compassion. It is a reminder that some questions are philosophical on purpose. Still, the exercise earns its keep because it forces care with language. It makes you ask what you mean by you, by continuity, by expectation, by most, and measure. It highlights how interpretations trade comforts. Many worlds grants a single, clean evolution but scatters identities. Collapse, theories, restore a singular story, but must explain the moment of selection. Relational accounts. Let facts be local to frames, and demand that agreement be earned by interaction. At each turn, the physics stays precise, while the meanings stay provisional. The universe keeps its numbers. We negotiate our narratives. There is comfort to take, if you want it, in the ordinary testimony of life. In our shared world, improbable survivals are rare. Aging is universal. Endings happen. Grief makes sense because it is not usually undone by secret strands. The same quantum theory that inspires these night thoughts also powers MRI scanners, atomic clocks, lasers in operating rooms, and the electronics that carry voices across oceans. Every successful prediction anchors trust that the familiar patterns will continue in the morning. Your coffee will steep. Your shoes will remember your feet. The lamp will glow when you press the switch. Meanwhile, the quiet questions remain, not as threats, but as invitations to humility. If a Cheshire grin can favor one corridor, while footsteps favor another, if distant answers can coordinate without a whisper, if later choices can help decide which earlier patterns count as waves or particles, then perhaps the self we carry is also less like a pebble and more like a braid, information and memory and body, woven tightly enough to hold shape through most of what the day brings, but still a weave, not a single strand. In such a world, even the wildest thought experiments can be set lightly on the nightstand, noted for what they reveal and what they do not. Keeping the lights low, the guiding principle is simple and human. Speculations belong on paper. Lives belong in care. The brain loves puzzles, and it is welcome to them. The rest of you deserves gentleness, sleep, and the steadying fact that in almost every branch that matters to a heart, meaning is made in company, by people who show up, by routines that keep time, by promises kept across days. The universe may be stranger than we hoped and more dependable than we feared. Between those two truths there is room to breathe, to rest, and to let the hard questions idle softly until the sun comes in. Set gently on the nightstand. That uneasy thought experiment still earns its keep. It shows how strange quantum ideas can become when they brush against the first-person view of a life. It asks our favorite interpretations to follow their own lines all the way to the edge and then tell us what the view looks like. Physics is not only about particles and forces in the abstract. It is about reality as it is lived, eyes that observe, minds that model, people trying to make sense of a universe that is, at its base, quantum. Whether quantum immortality is a faithful consequence of branching worlds or a misfire that stretches quantum reasoning past its remit, remains a live argument. The very fact that careful thinkers keep circling it tells you how deep the questions go. We are no longer asking only what electrons do. We are, in a quiet way, asking what we are. From the self, the mind turns toward information itself, and a clash as stark as any in modern theory. Imagine two champions who have never lost a match, quantum mechanics and general relativity, stepping onto the same court. Each plays perfectly in its own league. Put them together near a black hole, and the rules collide. A black hole, in simple outline, is what may remain when a massive star spends its fuel and gravity wins the long tug of war. The collapse rushes past every known pressure. Matter is driven into a region so tight that the familiar laws cannot describe the interior. The mathematics of relativity sketches a singularity there, a place where density runs to infinity and our current language breaks. Around that unknown core sits the event horizon, a not-quite surface with a simple rule. Cross inward, and every future path points deeper in. No light, no signal, no cry returns to the outside. From far away, the horizon acts like a one-way membrane. Relativity is spare and elegant about such objects. A quiet theorem says that, as seen from outside, a black hole is fully specified by just 3 numbers: mass, electric charge, and spin. All the messy particulars, what fell in, how it was arranged, the tangled library of microscopic details are shaved away. People summarize that starkness with a phrase: black holes have no hair. Bald, smooth, characterized only by their basics. Quantum theory bristles at that baldness. In the quantum story, information is sacred. It cannot be erased. That is not a moral preference, but a mathematical fact. The evolution of a closed quantum system is unitary, meaning it is reversible in principle. Give me the final state exactly, and I can, in principle, run the film backward to the beginning. Nothing about the world's precise micro-description is allowed to vanish without a trace. Now, picture a book, a literal book, tossed toward the dark. It carries ordinary information in words, and also delicate quantum information in the exact states of its atoms. Cross the horizon, and by relativity's lights, it is gone from the outside universe. The black hole grows a whisper heavier. The details are lost to us forever. Quantum mechanics refuses to shrug. If information was in the world and is now nowhere accessible, where did it go? Is it stored somehow in the hole? If so, where, and by what mechanism? The paradox deepens when another quantum whisper arrives. In 1974, Stephen Hawking showed that black holes are not perfectly black. The quantum fields near the horizon seethe. Pairs of virtual particles flicker into being and normally erase themselves. Very near the boundary, one partner can fall in while the other escapes to infinity. The trickle of escapees is Hawking radiation, and it carries energy away. Over a time so huge it dwarfs the age of the universe, an isolated black hole would evaporate completely. This is theory, but it is clean theory, built from tools trusted elsewhere. Hawking's original calculation says that radiation is thermal featureless in the way a perfect glow from a hot stove is featureless. A thermal spectrum tells you temperature and little else. If that is right, the outgoing light carries no imprint of the book, no code for the teacup, the astronaut's glove, or the poem you hurled past the horizon. Wait long enough, and the whole is gone, replaced by a bath of bland heat. The information that once existed is not hiding, it is destroyed. That is a direct break with quantum law. Two undefeated champions, one game, they cannot both win. If information can truly be destroyed by black holes, then quantum mechanics is wrong in its bones and must be rebuilt. If information cannot be destroyed, then something about Hawking's clean derivation or about the space-time picture of the whole is missing an ingredient. This is not a minor footnote. It goes to the heart of what lawful evolution means. Across the decades, many rescue lines have been thrown. One sober possibility is that the radiation is not perfectly thermal after all. Perhaps, buried under the smooth curve, there are correlations, tiny, exquisitely scrambled dependencies among the outgoing quanta that together encode everything that fell in. Think of a message shredded and scattered across an unimaginable number of bits. Any small handful looks like noise, but the whole pile contains the text. This idea has gathered strength. In advanced frameworks string theory, holographic dualities arguments point to information escaping in the radiation. The black hole, from this view, is an extreme but lawful mixer. It scrambles information rather than killing it. Even here, puzzles remain. Timing matters. If information rides out only at the very end, when the whole is a wisp, how does it get from the deep interior to the lip in time without breaking relativity's speed limit? If it leaks out gradually, beginning halfway through the life of the whole, in what pattern does it emerge? And how do we reconcile that with the clean thermal look of early radiation? There is a famous page in this story, the page time, named for Don Page, marking roughly when information must begin to come out if unitarity is to be saved. Past that time, the outgoing radiation must be more than hot light. It must be a ledger, entangled in precise ways with the radiation already emitted, proving that in a full realistic model is hard work. Showing exactly how the ledger is written is harder still. Other ideas have had their seasons. Maybe the information is stored on or just outside the horizon itself, in a kind of holographic skin that keeps track of what fell in and dribbles the record back out, a viewpoint encouraged by the surprising way black hole entropy scales with horizon area rather than volume. Maybe the interior and the exterior are not independent in the way naive pictures suggest, so that what looks like inside information can be recovered outside without violation. Maybe there are subtleties in how semi-classical gravity, the method used in Hawking's calculation, quietly fails near horizons, and the failure comes exactly where bits would otherwise be lost. And then there are proposals designed to make you sit up in bed. If the radiation truly carries detailed information out, then late-time quanta must be extremely entangled with early ones. Combine that with the requirement that nothing special should happen as you fall through the horizon, the equivalence principle, and you can be driven into contradictions. One dramatic fix is to say that something is special at the horizon, a firewall of high-energy quanta that destroys infalling observers. That move preserves unitarity and keeps the radiation's correlations clean, but it tears at relativity's promise that, locally, free fall should feel ordinary. Most researchers hope for a gentler resolution that saves both unitarity and the quietness of horizons. Beneath the flurry, a common thread has become hard to ignore. Information matters in gravity, in a way we did not expect. Entropy counts horizon microstates. Geometry may be emergent from entanglement in certain dual descriptions. No hair is less bald than advertised. If hair means fine-grained quantum structure, accessible only in global delicate measurements. The exact dictionary is unfinished, but the hints line up. The universe seems less interested in destroying information and more interested in hiding it creatively. For a bedside reading of the paradox, a soft metaphor will do. A black hole is less like a trash fire and more like a perfect shredder that also, in principle, outputs the confetti. You would need to reconstruct the original document if only you could gather every scrap and know the exact way they fit. At first, the confetti looks uniform. As the bin fills past a certain point, structure in the pile encodes more and more of what went in. None of this violates the second law. None offers a practical way to rebuild a novel burned long ago. It says only that the world's bookkeeper does not forget, even when we cannot read the ledgers. What remains true through every twist is the tone we started with. Quantum mechanics keeps its promises about information unless we have excellent reason to think otherwise. And general relativity keeps its promises about smooth space-time until the quantum insists on a correction. The paradox is not a failure. It is a lantern hung where new road must be cut. Somewhere in that terrain where horizons, entanglement, and geometry meet lies a clearer view in which what goes in and what comes out harmonize again. Until then, the story is enough to sleep on. A star collapses, a horizon forms, the outside world watches a slow, cold glow seep away. The radiation looks simple, but the simplicity may be a mask for a pattern only the whole sky could decode. The book you threw is not burned to nothing. Its words are scattered in a language we do not yet speak. The theories that brought us here are not enemies. They are instruments tuning to the same key. And somewhere beyond the edge of the lamp's circle, a better melody is waiting. One that keeps causality calm, keeps unitarity whole, keeps the fall through the horizon uneventful, and keeps faith with every experiment we have ever done. One path toward calm goes by way of a startling idea with a gentle metaphor, a hologram. The holographic principle says that everything needed to describe a chunk of space, the full catalog of its tiny details, can be encoded on the region's boundary, like a two-dimensional plate that contains the recipe for a three-dimensional scene. For black holes, this picture turns the event horizon into more than a border. It becomes an information surface. Each bit of detail adds a tiny patch to that surface. As matter falls in, the horizon's bookkeeping grows. As Hawking radiation trickles out, the bookkeeping can, in principle, leak back into the outgoing light. Elegant and unnerving at once, the idea has come to sit at the center of modern theory, hinting that space may be emergent, a pattern woven from information rather than the loom itself. The mathematics offers strong support, but the mechanism is still misty. By what precise choreography is the interior's story written onto the horizon? And how is that script then copied into the radiation that escapes? Another turn in the maze arrived in 2012, when a group of theorists, often labeled apes, argued that you cannot keep every promise at once. If the radiation really carries information out and quantum rules stay consistent, then the region just outside the horizon cannot remain as quiet as relativity says. To satisfy all the entanglements that unitarity demands, there would have to be a firewall, a sheet of searing quanta waiting at the horizon, incinerating anything that falls. That move saves information but breaks the equivalence principle that says a freely falling traveler should feel nothing special at the horizon. The fix looks like a flare, bright, decisive, and difficult to reconcile with the serene geometry outside. Not everyone accepts the fire. Some say the assumptions are too rigid. Relax a few, and the contradiction loosens. Some suggest the drama is observer-dependent. What looks like a wall of heat to one description remains gentle to another, with no single view owning the truth. Others work to reinterpret the wall in subtler terms that keep free fall uneventful, while still threading information through the radiation. Each patch introduces its own snags, typical of deep physics, where resolving one tension can tug another string loose. When two undefeated theories disagree, reconciliation often requires a new instrument, and that instrument must play cleanly with the whole orchestra. Many hope the right instrument is a full theory of quantum gravity. String theory has given crucial hints, precise counts of black hole microstates, matching horizon entropy, dualities in which a gravitating bulk is mirrored by a boundary theory without gravity, making the holographic slogan mathematically concrete. Loop quantum gravity offers a different toolkit, quantizing geometry itself and suggesting that areas and volumes are built from discrete quanta. Others suspect we will need something even stranger, perhaps a rewrite of what space and time are, with geometry emerging from networks of entanglement. There is bolder speculation still. Maybe information in gravitational settings follows rules more subtle than those of standard quantum information theory, forcing an extension of our cherished theorems when curvature is extreme. That would be a serious revision, but the paradox leaves the door cracked for possibilities we would not otherwise consider. What makes the black hole paradox so valuable is how far its lessons travel. Black holes are special because they press both quantum mechanics and general relativity into service at once. But the fix we find there will not stay local. It will reshape our understanding of time, space, and information across the board. We cannot fly to a horizon and drop books in to watch the letters re-emerge. The nearest candidates are thousands of light years away, and their evaporation times dwarf the age of everything we know. So we work with thought experiments, with consistency demands, with mathematics that has proved reliable in gentler arenas. We also build analogs on the bench, horizons for sound in superfluids, for light in carefully crafted media systems that share the same equations in miniature, and let us watch how patterns of information ride a boundary. From all this, a sketch has formed, not yet a portrait. The radiation likely is not perfectly thermal. Tiny correlations almost certainly hide within it. The horizon almost certainly carries information in a holographic way. The global evolution almost certainly keeps faith with unitarity. And still, the details of the ledger remain hard to read. How exactly does the page get written? When exactly does it begin to be legible after the page time? Gradually, or all at once in some late flourish? Can we keep the horizon smooth for falling travelers and still let the outside world recover every last bit, even in principle? The community holds different answers in careful hands, testing each for cracks. The larger lesson is humble and bright. Physics is unfinished. We built two staggering structures, quantum theory and relativity, and both keep their promises wherever we have checked. Black holes are where the seams show, where the stitches pull under stress. Mending those stitches will not be cosmetic. Whatever theory finally joins the fabrics will change how we think about reality in ways we cannot yet name. The way calculus once changed what motion meant, or thermodynamics changed what heat meant. The paradox is less a wall than a doorway. And through that doorway lies an even older riddle, the one that started this quantum path and refuses to be quiet. How does a blur of possibilities sharpen into a single outcome when we measure? We have wandered among horizons and holograms, watched information hide and return, and still, the most basic question curls at the edge of the pillow. A detector clicks, a needle points, a screen shows a dot. The equations flow smoothly before and after, but the moment of decision, what we call measurement, sits there like a small, bright stone in the stream. What exactly happens when the world chooses? What really happens when we look? In the calm, clockwork world we learn as children, a thing simply has its properties. You point a thermometer at the T, and it tells you a temperature that was already there. The most your looking can do is nudge the scene a little, in ways you could have predicted. Quantum mechanics whispers a different lullaby. Before a decisive look, a system is carried by a wave function, a soft ledger of possibilities, and their weights, so that an electron is not tucked at A or B, but spread across both. A shimmer of could be that interferes with itself like ripples on a pond. Then comes a single, definite click. A dot appears at A. We say the wave function has collapsed. A smooth swell of options draws tight into one outcome. The mathematics treats these two moods with separate recipes. Left alone, quantum states evolve gently and reversibly by the Schrödinger equation. This unitary flow preserves information like a melody carried perfectly from bar to bar. But the moment we measure, the formalism switches registers. The state jumps to a single result with a probability given by its earlier weights. That jump is not described by the same smooth equation. It is tacked on as the collapse rule. Two kinds of change. One theory that is the measurement problem in its most human phrasing. When, exactly, does the music switch from a glide to a snap? What makes a measurement a measurement? Pointing to a device doesn't end the story, because devices are made of atoms too. If you include the particle and the detector in one big quantum description, the mathematics says they should entangle and keep evolving unitarily together. No snap, no collapse. Yet in practice, we never see superposed needles or half-written numbers on a screen. A dial points, a pixel lights. Our notes in the lab book are not smeared across options. If the jump doesn't happen at the detector, does it wait for a mind? But minds are also arrangements of matter. Where would we draw the line? The puzzle is not that the theory fails to predict outcomes, it does, with absurd precision, but that the story behind the outcomes won't settle. Different temperaments keep different night lights burning. One is the Copenhagen mood. Treat the wave function as a tool tool for organizing expectations, not a real field sloshing through space. Quantum properties are not settled facts until you ask a well-posed question with a well-built classical apparatus. Collapse, in that spirit, is a bookkeeping update when information becomes available. It is practical and powerful, and also deliberately modest about what's really happening. It leaves blurry the border between quantum and classical, and many find that blur uneasy. Another lamp is the many worlds picture. Here there is no collapse at all. The wave function of the universe always flows unitarily, and what feels like a jump is the branching of the world into strands where each outcome is realized. You see A in one strand, another you sees B in another. No special rule for measurement, no exceptions to the equation, only a vast, quiet multiplication of stories. It is elegant in the mathematics and heavy in the imagination. If all branches are equally real, why does experience feel singular? Why do probabilities feel like chances rather than branch weights? There is also Bohm's pilot wave view. Particles always have definite positions, guided by a wave that stretches across space and steers them along precise paths. The wave never collapses. It is the wind. The particles are the boats. The tail restores a classical sense of what is where, but the guiding wind is unavoidably non-local, sensitive to faraway settings, and we cannot poke it directly. For some, that is a feature. For others, a high price. A gentler shift is relational quantum mechanics. States are not absolute. They are always about something relative to someone. You and your apparatus write one consistent story. I, watching both of you from outside, may write a broader story that keeps more superpositions alive until I interact. Facts are agreements reached when systems touch. Collapse, then, is not a physical thunderclap, but a tidy update inside each relationship. It trades a single world picture for a web of compatible perspectives. Objective collapse theories make the jump physical. They add a small, law-like tendency for superpositions to unravel by themselves, especially as systems get larger or more spread out. Microscopic things stay fuzzy. Macroscopic things fall into place. These models predict tiny deviations from standard quantum behavior, new constants, new noise that we can hunt for. So far, the hunts have only tightened the leash. No decisive collapse signal has appeared. And there are consciousness-based ideas, old and controversial, that put the mind back on the stage. Outcomes crystallize where awareness occurs. Most physicists step back here, not because the questions about experience are unimportant, but because the proposal imports a slippery concept into equations that prefer unambiguous parts. What counts as consciousness? A human brain? A mouse? A machine? The border risks becoming as vague as the one it hoped to replace. Threaded through all of this is decoherence, the quiet, physical process by which a delicate superposition entangles with its environment and loses the ability to interfere. A speck of dust, a warm detector, a whisper of air, each steals a little phase information and spreads it into countless degrees of freedom. The result is that, for all practical purposes, branches stop talking. The world looks classical. Decoherence doesn't choose a single outcome, so it doesn't solve the whole problem, but it explains cleanly why we never witness macroscopic blurs. It is the stagehand that dims the lights on interference and lets definite records stand. So what, at day's end, are we to believe? The mathematics works no matter which story you favor. Every laser and MRI and chip is proof of that. The debate is about meaning, about how to fit the formalism into a picture of reality that doesn't pinch. Do outcomes exist only when asked for, or always? In parallel? Are properties guided by a hidden wind, or stitched from relations, or selected by new physical rules we have not measured yet? There is no verdict that satisfies every taste, and it is all right that there isn't. Foundational work moves slowly because it is careful and because it knows the cost of premature certainty. What matters for a resting heart is a kinder truth. The uncertainty is not a failure. It is an honest boundary. We understand enough to build tools that heal, clocks that keep the world in sync, telescopes that listen to the first light. We do not yet agree on the deepest grammar of is and happens, and that is precisely where wonder lives. The measurement problem keeps our questions honest. It reminds us that looking is not a passive act, that questions and contexts help carve outcomes from possibility, that real may be more relational, more layered than the daylight mind prefers. If there is a closing image to keep, let it be simple. A screen in a quiet lab, a single pixel flickering to life. Before the click, a hush of options. After the click, a fact you can point to. Between them, no thunder, just a transition our current stories sketch in different inks. Somewhere ahead, a better story will join the inks into one line. Until then, we can rest inside a trustworthy strangeness, a universe that keeps its numerical promises and still invites us, gently, to rethink what it means to see, to know, to be. Let your breath match that rhythm. Soft possibilities in, settled outcomes out, and let the room and the questions grow quiet.